Hello, welcome to Engineers Mindset. So let's say we are given this table and we are asked to complete the following table for steam, entering dashes where appropriate. Okay, so let's examine the table. We have the column for mass. These are different values of mass for each of these tables. Okay, we have the column for pressure in bar. So the first pressure is simply 5 bar. The first mass is given as 0.8. Okay, so these are different. These are the columns and rules of the pressure. We have the next column for saturation temperature in degrees Celsius. Okay, so we have value here. We do not have values here. Okay. Next column is for volume in meter cube. These are values of volume. Same thing here. We'll have for dryness fraction. Okay. We have for dryness fraction. We have for degree of superheat. We have for degree of superheat. These are different values for degree of superheat. Okay. We have for enthalpy. Okay, this is column for enthalpy. And then we have finally for internal energy. This is total enthalpy. This is also total internal energy because they are all in kilojoules. Okay, so we have this. All right, so we have to fill in what these other spaces down filled. Okay, so we definitely have to work with the steam table to be able to do this. So for the first table or for the first row, we have the mass was given as simply 0.8. So let's get down those properties. For the first row, we have mass M was given as 0.8 kilograms. Okay, we have pressure. Pressure is given as 5 bar. We have pressure as 5 bar. Okay, P equals 5 bar. We don't have the saturation temperature. We need to find it. We also need to find the volume. We also need to find the dryness fraction. We also need to find the degree of superheat, the enthalpy, and the internal energy was given as total internal energy is 1977 kilojoules. So internal energy was given. Okay, U simply 1977 kilojoules. So it's not specific, it's total. All right, so let's start with what the next column there, which is temperature column. We need to find the temperature in degrees Celsius. So all we need to do is go through the steam table, look for the temperature that corresponds to this given pressure of 5 bar. Okay, let's check it out. Okay, so this is our steam table. Please, you go to saturated water and steam. You go to saturated water and steam corresponding to this is, let me zoom it up a bit. All right, so this is saturated water and steam corresponding to the given pressure there is 5 bar. Okay, pressure there is 5 bar, so corresponding to 5 bar. So this is column for pressure. All right, this is column for pressure. You trace out 5 bar, trace out this is 5 bar. We're looking for the temperature corresponding to that point. Remember, after pressure, the next column there is temperature in degrees Celsius, as can be seen. Okay, so locate temperature in degrees Celsius directly here. 5 bar. Yes, we simply 151.8. Okay, so which means saturation temperature there. So which means the saturation temperature there is simply 151.8. All right, so T saturation at 5 bar, saturation temperature is equal to 151.8 degrees Celsius. So it means what we'll have here is actually 151.8. That gives us the temperature and that pressure. Next thing to find is the volume, and of course we know that to obtain the volume, okay, the relationship between volume and dryness fraction, recall that total volume V is simply what the mass times the dryness fraction times the volume at gas, the volume of the gas at the given pressure. So that's Vg. From the question, we weren't given dryness fraction, which means we need to obtain dryness fraction. Okay, which means we need to obtain dryness fraction. To do that, we were given total internal energy as 1977. Now recall that the relationship between dryness fraction x, and internal energy is simply what? Specific internal energy, which is U, minus internal energy at the fluid all over UFG. Okay, internal energy at the fluid and gas. So this equation can also be written as U minus UF all over UG minus UF, because UG minus UF simply gives us UFG. So all we need to do now is, first of all, the internal energy that was given to us is total. So we need to convert that internal energy to specific internal energy. Okay, so from what was given to us, internal energy here is simply 1977 kilojoules. Okay, so from U equals 1977 kilojoules. All right, you can convert to specific. Okay, if you convert this to specific property, now it becomes specific internal energy. Therefore becomes U divided by mass. That's simply equal to 1977 all over the mass was given as 0.8. So all over 0.8. This simply implies that specific internal energy U is simply equal to, okay, so we have 2471.25 kilojoules per kilogram. Now the reason why we converted this is simply because every property at the steam table is simply what? A specific property. So which means we also have to convert this to specific property, so we can use this formula to find the dryness fraction. Okay, so having known this now, dryness fraction x. Okay, so first of all, we need to now obtain the values of UF and UFG corresponding to what? This pressure 5 bar. All right, so from saturated water and steam, corresponding to 5 bar, that's the given pressure. Okay, so we obtain what UG is. Let's dive into our steam table. Okay, so here we are. Also 5 bar, not forgetting. This is the column for the pressure, and this is the column for um, enthalpy. This is column for entropy. Why? This column for volume, specific volume. This column for specific internal energy. So as you can see here, it's in kilojoules per kilogram. That's why we have to convert that total internal energy to specific, because all the properties of the steam table are all specific properties. Okay, so we have here, this is UF, so which means all the values here are what? Internal energy at the fluid. This is UG, all the values here are internal energy at the gas. So we are looking for now 5 okay, so we're looking for 5 bar. This is pressure of 5 bar. Okay, so let's trace it now. So I think here. Okay, so this is UF. Yes, that's UF. The value is 639, and UG is simply 2562. Okay, UG is 2562. So UG at that pressure is simply 2562. UG is 2562 kilojoules per kilograms, and UF itself, okay, UF is simply let's get it out. 5 pound 639. UF is 639. Okay, so we have UF to be 639 kilojoules per kilograms. All right, so if we know this now, we can now find the value of the dryness fraction. Of course, UFG itself is simply UG minus UF. So that means UFG is simply, UG is giving us 2562. So simply have 2562 minus UF is giving us 639. 639. So this simply implies that UFG is now equal to 1923 kilojoules per kilogram. So we can now employ the ratio or the relationship to find dryness fraction. Okay, here, so x, therefore dryness fraction x is equal to specific internal energy minus internal energy at the fluid all over UFG once more. which implies X is equal to specific internal energy. We obtained that earlier. That's total internal energy divided by mass, and that value simply gives us 2471.25. So we simply have 2471.25. This is 2471.25 minus UF, which is specific internal energy at the fluid, and UF simply gives us 639. We have 639 all over UFG, which we've obtained here to be 1923. 1923. Okay, so therefore X is now equal to, so let's get 2471.25 minus 639, 1832.25 divides by, okay, 1923 divides by 1923. So we have this. So this simply implies that Dryness fraction X is equal to, so this divides by this, divides 1923, that's simply 0.95. So Dryness fraction is 0.95. Okay, so if we have this, we can fill the column for Dryness fraction. Okay, 0.95. Okay, Dryness fraction X is simply 0.95. Okay, so we can now obtain the value for the volume. Alright, so to obtain volume, total volume V is simply mass times Dryness fraction times volume at gas, Vg, corresponding to that pressure. So we look from saturated water and steam now. From saturated water and steam, corresponding to the given pressure at that row, that is simply 5 bar. Let's obtain what is Vg. Okay, Vg is equal to, okay, so back to the steam table. Okay, this is 5 bar. This is coulomb for pressure. Okay, coulomb for pressure. This is 5 bar. The next row there is for temperature. Finally, the next row as the third row is for volume and the gas, as can be seen here. So corresponding to 5 bar, volume is simply 0.3748. Alright, so Vg is simply 0.3748. 0.3748. Take this down a bit. Okay, which is simply 0.3748 kilojoule, sorry, meter cube per kilograms. So we have this. Alright, so this now implies that if we now employ this formula, total volume V is now equal to mass of the fluid was given as the mass was given here as 0.8. Okay, for that first column, mass is 0.8 multiplies by, we said Dryness fraction, we obtain Dryness fraction here 0.95, so multiply 0.95. Okay, multiply volume of the gas and that given pressure, and that is simply 0.34, and that's simply 0.3749. We have 0.3749. So this simply implies that total volume of the fluid is simply given as 0.28 meter cube. So that gives us a volume at that given pressure. Okay, that's the volume of the steam. So the column for volume is simply 0.28. Okay, next is to find degree of superheat. Okay, all right. Okay, so degree of superheat okay is simply DOS is simply given as superheated temperature minus saturation temperature. Okay, so we already know saturation temperature at the given pressure. Now, since specific internal energy, we obtain specific internal energy U when we divided the total internal energy by mass, and we obtained this to be 2471.25. Okay, our specific internal energy, we obtained that to be 2471.25 71.25 kilojoules per kilograms. So please, the reason why we're using that is simply because from the beginning of the question, that was the only thing that was given to us from on the table. Okay, so we converted it to specific property. So we have to go and check the temperature corresponding to this property from the superheated steam table. That's the temperature we use towards subtract the saturation temperature. So that's why we're using it. Okay, because that was the only condition that was given to us on the table to find. Okay. Alright, so I said we have to convert this internal energy to specific property because all the properties on the steam table are all specific properties. That's why we needed to convert this to specific property. Now, all we need to do is go to the superheated steam table. We now have to look for the temperature corresponding to this internal energy from the superheated steam table. Okay, already we know saturation temperature at 5 bar. Okay, at 5 bar from saturated water and steam. We obtain saturation temperature simply as 151. Okay, we obtain that simply 151.8 degrees Celsius. Okay, we obtain that as 151.8 degrees Celsius. So now we look up the superheated steam table. From superheated steam, corresponding to this internal energy now, U equals 2471.25 kilojoules per kilograms. Okay, let's pull out the. Alright, now as always, steam table is divided into two. We have the saturated water and steam, which is here. Okay, we have the superheated steam table. This is superheated steam. So we're looking for temperature corresponding to this internal energy 2471.25. All right, so once again, if you look at the superheated steam table, you notice that these are properties for total volume or volume of the gas. These are properties for internal energy. So after the volume, the next is internal energy, next is enthalpy, and then next is entropy. So these are internal energy for ranges from 25. So if you check for you see down 259, this is also 25 from 25 to 6 and above. Okay. Meanwhile, these are internal energies from 24. So which means all the parts of internal energy are ranges from 24. Alright, so to find the internal energy corresponding to 2471, which is what we're looking for, which means it actually fell here. This is 24. Alright, so we start these at different temperatures corresponding to that internal energy. We have 10 degrees, we have 100 degrees, 150 degrees, and all that. Okay, so we are looking for 24. This is internal energy 2443. We're looking for 2471, and after 2443, the next here is 25. So which means 247 actually is in between. This is 2443. That means before we get to 247, it has to be in between these two, because after here you will not see. After here you can never see any 24 again. This is 249, and 249 is highly above. Okay, you can see here is 25. So after this position you can never see 24 again. So which means 2471.25 actually lies between these two internal energies. Okay, and these two internal energies have temperatures here, 10 degrees and 100 degrees Celsius. Okay, so we'll have to interpolate to obtain the value. All right, so let's try that and see now. So we had 2443 and 2516. Okay, so let's interpolate now. All right, so these are the internal energies we have. We had 2443, and we are looking for temperature corresponding to 2471.25. And then we had take this up a bit, 2516. Okay, and then we have 2516. Okay, so we had this. All right, so we need now temperatures. The temperature corresponding to 2443, we know that. Let me take it up a bit. So this is 2443. Temperature corresponding to this is simply what, 10 degrees Celsius, and this is 2516. Temperature corresponding to this is 100 degrees Celsius. So their temperatures is simply, this is 10 degrees Celsius. Take this down a bit. So this is 10 degrees Celsius. Okay, 10. This is what we're looking for, unknown superheated temperature. Okay, and this is 100 degrees Celsius. Now this is how you interpolate. A very easy way to interpolate. I could choose to use the last value to subtract everything. So any energy I maintain here, I must also maintain the same energy here. Okay, so let me use the last value here to subtract everything here. So I simply have 2516 minus let's say 2443. So since I used this last value to subtract the first value, it means I must also use the last value here to subtract the first value. So the last value here is simply 100 minus first value here is 10. So I have this all over. Same thing here, 2516 subtracting this. So you can as well use this minus this or this minus this, whichever way gives you the same answer. But this is like easier. So I use 2516 to subtract this. 2516 minus this is 2471.25. 71.25. So this is also going to be, since I use this to subtract this, it means I will also use the last value here to subtract this. So I'll simply have 100 minus superheated temperature, which is what I'm looking for. Alright, so let's evaluate that and see. Okay, so 2516 minus 2443 actually give us 73. So we'll simply have 73 all over here. 2516 minus 2471.25. That simply give us 447.5, and this is equal to, so I have here 100 minus 10, which is simply 90 all over. So this remains 100 minus superheated temperature. Okay, so I will make it easier for myself. I will simply divide these two. So 73 divided by 447.5, or you may choose to cross multiply. It's still the same thing, but I choose to go the easier way. 73 divides 447.5. Okay, so that simply gives me 1.63. This is equal to 90 all over 100 minus superheated temperature. Okay, so this is same as saying 1.63 divides by 1. Okay, it's the same thing. Of course, 1.63 divided by 1 still remains 1.63. At this point now, I will simply cross multiply. 1 multiplies 90, so that I did this to avoid too much numbers, because if I had done 447.5 multiplied 90, it would have been a bigger number compared to this. So at this point, I'll simply have 1 multiplied by 90, and I'll have 1.63 multiplied by the whole of this value. So I'll simply have here 1 multiplied by 90, and that's simply equal to 1.63 multiplying by the whole of this value, 100 minus superheated temperature. So I simply have 100 minus T superheat. Okay, so this is simply, of course, 1 by 90 simply remains 90, and this is equal to 1.63 multiplied by 100 simply gives us 163 minus, this is 1.63 T superheat. Of course, if you expand this with this bracket, of course, if you expand the bracket with this, it becomes 1.63 times 100 and 1.63 times T superheat. Okay, so of course, we are looking for superheated temperature. So let's simply send 163 over here. It becomes 90. Positive sign crosses and equal to sign becomes negative, minus 163, and that's simply equal to, I'm left here with minus 1.63 T superheat. Okay, of course, 90 minus 163 simply gives us um, minus 73. And that's equal to minus 1.63 T superheat. Alright, so to make superheated steam subject, we simply divide both sides of the equation by minus 1.63. Therefore, superheated temperature is simply minus 73 divides minus 1.63. So this simply implies that T superheated is actually 44.78 degrees Celsius. Okay, this is a little bit lower than saturation temperature, so it means we are going to obtain negative value. Alright, so degree of superheat is simply superheated temperature minus saturation temperature. So this simply implies DOX is equal to superheated is 44.78 minus saturated temperature is 151.8. So we are getting a negative value 151.8, which means the degree of superheat is actually okay. That's simply minus 107.02 degrees Celsius. Okay, I'm guessing we are having a more saturated steam than it is superheated. I think that's why you're having negative. But yeah, that's it. Minus 107.02. So that's the column for this. Minus 107.02. Okay. Finally, for this column, we have to find okay. We have to find the enthalpy. Okay, so you know enthalpy, specific enthalpy H is simply equal to um, enthalpy at the fluid plus dryness fraction times HFG, enthalpy at the fluid and gas. So let's obtain this now. We know dryness fraction X. Of course, we can find enthalpy at the fluid. So from 5 bar, okay, from saturated water and steam, okay, and steam corresponding to 5 bar, okay, we'll obtain HF to be equal to, let's look up now the steam table. All right, so once again, this is column for okay enthalpy. So you can see here enthalpy at the fluid HF, enthalpy at between the fluid and the gas. So this is actually HFG and not HG. Okay, and this is HG, enthalpy at the gas. All right, so we're looking for 5 bar. Okay, so please just to get this out. All right, so this is 5 bar here. Okay, this is 5 bar. All right, so let's try and get the enthalpy lane. Okay, okay, I think here. So this is HF corresponding to 5 bar. The value is simply 640. Yep. Okay, so HF is 640 and HF is the middle one. Okay, 640. HF is 2109. Okay, so HF is 640. HF is simply 640 kilojoules per kilogram. HFG is 2109 kilojoules per kilogram. So we have this. All right, so we're looking for specific internal energy H, and that's equal to, so we said HF, which is 640 plus we have X, HFG. X is dryness fraction, and we obtained dryness fraction. Let me pull up the table at 0.95. Okay, we obtain that as 0.95. So this is simply 0.95 multiplies HFG. Okay, HFG, and HFG is simply 2109. 2109. Okay, so which means specific enthalpy is simply equal to 640 plus. So we have 0.95 multiplies 2109. That's 2003.55. So if we add this together, it means specific internal energy is simply equal to, that's 264 3.55 kilojoules per kilogram. So once again, we need to convert this to total value, and total enthalpy is simply what? Mass times specific enthalpy, and the mass was given to us from the question as 0.8 kilojoules, as 0.8 kilograms. Okay, so the mass is 0.8 multiplied by 2643.55. So this simply means total internal, this simply means total enthalpy is now equal to simply 2114 points. We have 84. kilojoules. Okay, this becomes total enthalpy 2114.84. okay, let's put it up there. So we'll have 2114.84 kilojoules. All right, guys, the video is longer than expected, so I'm actually going to pause this here and I will do another video for the second column. Okay, that's what I will do because it's getting too long. All right.